morning. I am Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College. Today I will be taking the topic of point defects. Now, why would we want to study defects? Because the defects affect the properties of the material. Electrical properties are affected. All defects affect the electrical properties, especially the point defects. Then mechanical strength is affected by the defects. Then the optical properties change, magnetic properties are affected, and kinetic properties of the metal also get affected by these defects. Now, these defects, they are also known as imperfections in solids. If we see the ideal structure of this solid, then at every lattice point has exactly the same environment, or the position of the atoms which are forming the lattice, it is fixed. And any deviation from this ideal structure leads to the defects. And the reason behind these deviations can be either during packing of the ideal structure, an atom can get missed, or it can get displaced, or it may also take place by the thermal vibrations, because during the formation of crystal there are chances that the atoms, they may leave their least energy positions and they can move to the higher positions, leading thus to the formation of defects in the solids. Now, coming to the type of imperfections, they can be one-dimensional imperfections, which are also called point defects. Then one-dimensional imperfections can also be line defects, where dislocations can take place. Then these imperfections, they can be two-dimensional, like planar or area defects, or they can also be three-dimensional, that is the volume defects. Now, coming to the point defects. Now, one-dimensional defects, that is the point defects, they can be of two types. They can be stoichiometric defects or they can be non-stoichiometric defects. Stoichiometric defects are those in which the number of positive ions is equal to the number of negative ions. And these stoichiometric defects, they occur in the ionic crystals and they are categorized into two categories, that is the Schottky defect and the Frankl defect. And the second type is the non-stoichiometric defect, in which the number of positive ions is not equal to the number of negative ions. They occur in the non-ionic crystals and they are classified into two categories. They can be metal excess defects and or the metal deficiency defects. Now, again these metal excess defects, they are classified into two, the interstitial defect or the vacancy defect. And metal deficiency defect, it is also classified into two categories, that is the vacancy defect or due to the presence of impurity. Now, coming first to the stoichiometric defects, and the first stoichiometric defect is the Schottky defect. Now, this type of defect, it arises when certain points in the lattice, crystal lattice, they are unoccupied. They are also known as lattice vacancies. Now, in this case, you can see I am showing the NaCl crystal where this is the Na plus and Cl minus ions which are present in the first case, but here you can see that the positive and negative ions are missing from the crystal lattice, and the number of missing positive ions is equal to the number of missing negative ions. Now, here the one Cl minus is being missed from the crystal lattice and one Na plus is being missed from the crystal lattice. But the crystal as a whole is neutral because the number of positive ions is equal to the number of negative ions, or the positive charges is equal to the negative charges. Now, this Schottky defect, it generally appears in ionic crystals in which the positive and negative ions, they do not differ much in size. Then, because of this Schottky defect, the crystal is in a position to conduct electricity to a small extent by ionic mechanism. And when electric field is applied, a nearby ion moves to its lattice side to occupy the vacancy. When we apply electric field, then the nearby ion occupies the vacancy and a new vacancy is going to be created. Here again, a nearby ion moves to the vacancy and a new vacancy is created, and so on. So, the nearby ions can keep moving and new vacancies can be formed. And this process, it also results in the migration of the vacancy and thereby of the ion from one end to the other end of the crystal. It is the movement of the ion. Therefore, the electricity gets conducted across the whole crystal. These vacancies, this also enable easy movement of atoms or ions in the crystal, and this accounts for the phenomenon of diffusion in solids. Solids generally do not diffuse, but because of the presence of these defects, there are vacancies and the vacancies, they are moving. Therefore, it accounts for the phenomenon of diffusion in solids. And since in this case, positive and negative ions, they are missing from the crystal lattice, therefore, the density of the overall crystal decreases. So, this defect, it results in the reduction of density. Next defect, it is the Frankl defect. Now, this Frankl defect, it arises when an ion, generally the smaller the cation, it occupies an interstitial position. It leaves its original position and it occupies an interstitial position between the lattice points. Now, here I have taken the case since silver bromide, zinc sulfide, both of them, they show the Frankl defect. Here we can see that the smaller ion, that is the cation, it leaves its original position and it moves to the interstitial position, and here this position becomes vacant. Now, since this position is vacant, then again the nearby ion can move to its position and a new vacancy will be created. So, here since the positive and negative ions is same, number of positive and negative ions is same, so the overall crystal is neutral. And this type of defect, it arises in crystals where the negative ions are much larger in size than the positive ions. There is much difference between the size of the cation and the anion. And again, because of these movement of the ions, this crystal is also, this defect is also responsible for the conduction of electricity in crystals and for the phenomenon of diffusion in solids. Now, here we can see in a tabulated form the differences between the Schottky and the Frankl defects. Now, the Schottky defect, it is formed when oppositely charged ions, they leave their lattice sides and thus create vacancies. And Frankl defects, these are seen when the smaller ion, it's displaced from its lattice position to an interstitial site. In the case of Schottky defect, these vacancies are formed in stoichiometric units to maintain an overall neutral charge in the ionic solid. And the Frankl defect creates a vacancy at its original position and an interstitial defect at its new location. Here, the density of the solid crystal becomes less. But in the case of Frankl defect, there is no change in the density of the solid. And Schottky, it occurs when there is a small difference between the size of the cations and anions, whereas the Frankl defect occurs when there is large difference between the size of the cation and anion. Obviously, both of their diagrams are also different. Here there are missing cation and anion, and here it is a misplaced cation. Now, coming next to the non-stoichiometric defects. Now, in this case, the compounds in which the ratio of positive and negative ions present in the compound, it differs from that which is required by the ideal chemical formula of the compound. They are called the non-stoichiometric defect. That means the number of positive ions is not equal to the number of negative ions. And these non-stoichiometric defects, they are of two types: metal excess defects and metal deficient defects. Coming first to the metal excess defects. As the name suggests, the number of positive ions are going to be in excess, and this can take place in two ways. First, it can happen due to the anionic vacancies, and second, it can happen due to the presence of extra cations in the interstitial sites. Coming first to the metal excess defects due to vacancy. Now, in this case, I have taken example of NaCl. When we heat NaCl by the excess in the sodium vapors, then extra sodium, they get incorporated into the crystal, and this sodium atoms, they give rise to sodium ions and electrons, and the electrons which are formed, they occupy a position which was supposed to be occupied by an anion, and this electron is equally shared by the 6 cations, 4 on the sides on the plane, 1 above and 1 below, and therefore this electron, it behaves like a delocalized electron. So, in this case, a negative ion may be missing from its lattice site, leaving a hole which is occupied by an electron, thereby maintaining an electrical balance. Now, these electrons, they are called as F centers or the color centers or the Farb centers, because they are responsible for imparting color to the crystal. Light is absorbed when this electron makes a transition from ground state to the excited state. Now, suppose this is the ground state, this is the excited state. When this electron, it absorbs light, it moves from ground to excited state by taking energy, and when it comes back, it re-emits light, and therefore this type of defects shown by the compounds, they impart color to the compounds. Since it is going to re-emit light, therefore NaCl of this type has acquired a yellow color. Now, in this case, excess metal causes NaCl to appear yellow. Now, when this NaCl, it is heated in an atmosphere of sodium vapors, as I said, the excess of sodium atoms, they get deposited on the surface of the NaCl crystal. The chloride ions then diffuse to the surface to combine with the atoms to form NaCl again. For this combination to happen, the sodium atom should ionize to Na plus. and the electron released during the ionization diffuses back into the crystal and it occupies the vacant site created by the migrating Cl minus ions. And then this electron absorbs white light and therefore the NaCl, it appears yellow in color. Similarly, lithium chloride, it appears pink, and potassium chloride, it appears violet in color. Next type is by the presence of extra cations in the interstitial site. Now, metal excess can also be obtained by having extra cations in the interstitial sites. Increased positive charge is balanced by the presence of extra electrons in some of the interstitial sites. And this sort of defect, it is similar to Frankl defect, in the sense that ions are present in the interstitial site, and thus such defects are found in crystals having Frankl defect. Now, I have taken the example of zinc oxide. When zinc oxide is heated, it loses oxygen and it turns yellow. By the reaction, zinc oxide from zinc ions releases oxygen and releases the electrons. Now, these excess zinc ions which are being formed, they are trapped in the crystal structure at the interstitial sites, and the electrons which are being produced, they also diffuse into the crystal to occupy the interstitial sites. Now, here this is the crystal metal excess defect due to anionic vacancy, which I have already taken. Now, this is the metal excess defect due to presence of interstitial cation. Now, here A plus is the cation which represents the zinc in this case, and B minus, which is the anion, represents oxygen in this case. Now, in this case, since zinc ions and electrons, they are present in the interstitial position, they are present in the same interstices, and for the accommodation of these electrons, the oxygen, it gets eliminated from the system, therefore it appears yellow. And here again you can see the number of cations is not equal to the number of anions, the cations are more in number, therefore it is a metal excess defect due to the presence of interstitial cation. Next is the metal deficiency defects. Again, the metal deficiency defects, the first one is by cation vacancies. Now, the metal deficiency defects, they occur due to the presence of less number of positive ions than the negative ions, and they can arise in two different ways. In some crystals, the positive ions, which are the cations, they may be missing from their original lattice points, and thus the vacancy is going to get created, and there will be extra negative charge in the system, and this negative charge will be balanced because the crystal as a whole has to be neutral. Therefore, this extra negative charge, it can be balanced by the presence of cations in the higher oxidation states in some neighboring sites. Since the same metal ion should have higher charge or the higher oxidation state, these defects are generally possible in the metals which show variable oxidation states, that is the transition elements. Therefore, some compounds which show this type of defects are iron oxide, iron sulfide, nickel oxide. Now, here you can see, for example, in the case of iron oxide, here the Fe is present in +2 state and oxygen is present in -2 state. But since at one of the places the cation is absent, that means Fe +2 is absent from the system. That means the neighboring two cations should occupy a higher oxidation state. They should be present. If I take the case of iron, if this is A is iron, then in this case this Fe plus 2 is absent. So, 2 of the neighboring Fe plus 2, they should acquire Fe plus 3, they should be present in the ferric state so as to maintain the electrical neutrality. This type of crystal again causes a decrease in the density because this vacancy will be left out. Then next type is the impurity defect in ionic solids. In ionic solids, the impurities are introduced by adding impurity of ions. If the impurity ions are in the different oxidation state from the host ions, vacancies are created. Now, these impurities which are present, they should be exactly of the same size of the metal, but they should be in the higher oxidation state. For example, the addition of strontium chloride to the NaCl. Now, here we can see that Na plus Cl minus, but here Sr plus 2 Cl, again there are 2, so Cl minus, 2 Cl minus. So, here the impurity is of the same size, but it is present in the higher oxidation state, whereas sodium is in the plus 1 oxidation state. So, where these strontium ions, they occupy these lattice points of sodium ions, and for the every introduction of these strontium ions, there is going to be removal of the 2 sodium ions to maintain electrical neutrality, and as a result one of the lattice point is occupied by the strontium, whereas the other one is going to be vacated, or there will be vacancy, it will be left unoccupied. In this case you can see Na plus Cl minus, but in the case one Na plus is being occupied by Sr2 plus. To maintain the electrical neutrality, this vacant site will be left out, and because of the introduction of impurity of the same size but of higher oxidation state, and these vacancies result in higher electrical conductivity of the solid. They can function as p-type semiconductors. And the another example is the addition of cadmium chloride as an impurity to the silver chloride. Here again the cadmium ions occupy some of the lattice points of silver ions, and since silver ions are present in the plus 1 oxidation state, but the cadmium ions, they are present in the plus 2 oxidation state. So, for every cadmium which is to be incorporated into this crystal lattice, there should be removal of 2 Ag plus ions from the system, so that electrical neutrality can be maintained. Thank you.